In this video, I want to talk about how the design of more FSMs and Mealy FSMs can be different. So to get to this point, let's just go over a simple example. So we have this snail that is walking past a bunch of zeros and ones. So our input to the system is something like this. And we read the input one by one. So at the rising edge of the clock, we read one of these bits. So this snail is trying to detect a pattern of 0 followed by 1. So for example, if we pass this sequence of zeros and ones to the system or to the snail, it should detect this 0 followed by 1, this 0 followed by 1, this 0 followed by 1, and this 0 followed by 1. So if we assume that we have A as the input bit at any clock edge and Y as the output bit, any time that we have a 0 followed by 1, the output is going to be 1. So since we are reading this sequence 1 bit by 1 bit, we need to know what was the previous bit, right? So we need to have some sort of memory, and that's why we use a sequential circuit to achieve this functionality. So before I continue, let's just quickly go over the differences that we had for the Moore and Mealy FSMs. So we had, for the Moore FSM, we had this next state logic unit that accepted the inputs and the current state as its inputs, and based on those, it was calculating the next state that we needed to store for our system. Then we had this register which contains several D flip-flops for storing the current state in our system. As for the output logic, we use the current state of the system, and we use this combinational circuit to calculate the outputs of the system at any given time. For Mealy FSMs, we said that the main difference is the way that we calculate the output logic unit. So while for the next state logic unit, we still have the inputs and we still have the current state of the system to calculate the next state, even though the internal part of this circuit and this one can be different. However, for the output logic, not only we use the current state of the system, but also the current values of the system as well. So if you pay close attention, you see that for the Moore FSM, the outputs are completely in sync with the clock. Why? Because the outputs are only dependent on the current state, which is synchronized with the clock. While for the Mealy FSM, while states are synced with the clock, but inputs are not necessarily synced with the clock. So for example, if you provide the input yourself at different times, since we don't have any control over the time that the input is being provided, the output logic can change accordingly as well. While for the Moore FSM, to change the output, the only path was going through the input, the next state logic unit, and the register, which was synced with the clock. While for the Mealy FSM, there are two paths that can change the output. So while you might say, okay, what is the point of this circuit? The point is that sometimes it is preferred to use a Mealy FSM because we can see the effect of changes faster at the output, even though having this extra pass doesn't affect the circuit to be still considered a synchronous sequential logic circuit. So now let's just go over the different steps that we need to take to design the circuit that we want using both Moore FSM and Mealy FSM. So if you remember from before, after identifying the inputs and outputs for our FSM, the next step would be to come up with the state transition diagram. So for the Moore FSM, we started from state 0, we called it S0, and we presented the outputs inside the circles. So at S0, which happens whenever we reset the system, the output is going to be 0 because we didn't detect any part of the pattern that we want. So now let's just say we are in this state and we detect a 1 as the input. So when A is 1. So when A is 1, since the pattern that we are looking for is a 0 followed by a 1, we basically haven't detected any part of the pattern yet because this order is important for us. We are looking for a 0 followed by a 1. So if we detect a 1 or A being true, we go back to this state. Nothing still hasn't happened. On the other hand, if we detect a 0, we can go to the next state, which is basically a representative of having detected half of the pattern. Even though the output is still 0 because we haven't detected the full pattern that we are looking for, but still this state is different than this one because this is representative of detecting half of the pattern, while this one was representing not detecting any part of the pattern. So now let's say we are in this state, state 1. What happens? What should we do if we detect a 0 as the input? Or let's say we have detected this 0 because we started from here, we detected the 0, we went to a state 1, and then we have another 0. We basically don't need to do anything. We need to stay in this state, right? Because having 1 0 or having a bunch of zeros consecutively still count as a part of the pattern. It still is different than the initial state that no part of the pattern was detected. Because when we detect a 0, now we are looking for a 1. So as long as we are detecting 0, that means that we can stay here. So this is for a bar being true. On the other hand, if we are in this state and we detect a 1, then we can go to the next state, which is basically representative of having detected the pattern that we want. So because of that, when we are in a state 2, then the output can be 1, representing that we have detected the pattern. So now that we have this, we need to see where we should go after we got to a state 2. Because we want to detect all the patterns of 0 followed by 1 in our sequence. So what should we do if we detect a 0? Since if we detect a 0, that is basically half of the pattern, we can go to a state 1. On the other hand, if we detect a 1, we need to go to the initial state. So for example, let's say we have 0, 1, 0, 1. So if we pass this pattern, this sequence to our system, we need to detect 0, 1 and another 0, 1. So we have 2 detection. While if we had 0, 1, 1, 1, we only needed to have 1 detection, right? So these arcs are enabling us to ensure that we can detect all the patterns of 0 followed by 1 in our sequence. So this is the state transition diagram for the more FSM. Again, we use circles to show the state, we use arcs to show the transition. On top of the arcs, we provide the inputs, and inside the circle, we provide the outputs too. So now let's just see what we need to do to come up with the state transition diagram of the Mealy FSM. So I start from the same initial state, but now for the Mealy FSM, since the output is not only dependent on the current state of the system, but also the input that we get, we cannot put the output inside the circles. When we put the output inside the circles, we are basically saying that the outputs are only dependent on the states or the current states of the system. While for the Mealy FSM, as you can see, the outputs not only depend on the current state of the system, but also they depend on the inputs too. So because of that, we need to find a way to show the output on top of the arcs, because we use the inputs to represent the condition for which each one of these arcs or transitions happen. So we need to have the outputs on top of the arcs too. So the way we do it is we use a slash to basically separate the inputs on the left hand side and the outputs. So for us right now, we only have one input A and we only have one output Y. So one bit of input, one bit of output. So now let's just say we are at the state 0, and again state 0 is representing that we didn't detect any part of the pattern yet. So what happens if we detect a 1 as the input? Same as above, we stay in the same state. So here A is the input, representing that the input is 1, and Y is basically 0. So I can just show it like this: A/Y bar. Or since we only have one bit, I can just show it like this: 1/0. So this first one is showing the input, the slash is the separator of the inputs and outputs, and 0 is the output. What if we have A to be 0? Then we can go to the next state. This is S1. Here we have A to be 0, so I can just show it as A bar. As for the output is still 0, so I show it with Y bar, or I can just simply show it as 0/0. So these two representations are equivalent. So now we are at the state 1, which means that half of the pattern is being detected. So what should we do if we detect another 0? We should remain in this state. And this is similar to what we had above. So when we detect another 0, we stay here and the output is still 0. Now, what happens if we detect a 1? If we detect a 1, then we need to show that we have detected the pattern, right? So what we do basically is that we go back to the initial state. So we have detected 1 as the input, and we say that we have detected the input, say we have detected the pattern with this one here. So remember, this one is the input, the slash is the separator, this one is the output. So as you can see, by having this option to have the outputs not only depend on the current state, but also the current inputs that we have to our system, we were able to eliminate one of the states. So we don't have to create a separate state for which we can calculate the output. We can just simply provide the output or compute the output and then go back to the initial state of the system. And no matter what pattern you provide to these two systems, the result is identical. They all detect a 0 followed by a 1, right? The difference is, as I will show later on, is that the time that they detect this pattern is going to be different. So now we have come up with the state transition diagrams for both of these FSMs, both Moore and Mealy. So let's just follow the next steps for the Moore FSM first, and then we follow the steps for the Mealy FSM too. So do you remember what was the next step for the Moore FSM after coming up with the state transition diagram? So the next step would be to convert this state transition diagram to a state transition table. And for that, we also needed to come up with an encoding too. So here I used a binary encoding. For the Moore FSM, since we had 3 separate states, we need to have at least 2 bits to represent these 3 states. Using 2 bits, we can have 4 possible combinations, right? So we use only 3 of them to represent these 3 states. If you want to use a one-hot encoding, you can use 3 bits, for which at each state only one of these bits is 1. So I leave that up to you to come up with the functions for using a one-hot encoding. So now, based on this, we can create the encoded state transition table as well. So let's just fill out the encoded state transition table. We have when we are at the state 0, 0 or state 0, and the input is the output is going to be 0. When the input is 1, we go back to a state 0. When the input is 0, we go to a state 1. So 0, 0, input 0, that means that we go to a state 1. So this is this arc. Again, each arc in the state transition diagram, except this reset one, needs to be represented in the state transition table with at least 1 row. Then for this arc, we are at the state 0 or encoded 0, 0. The input is 1, we remain at the state 0. So this is going to be, this one is, this one is the state 1, 0, 1, because our encoding for a state 1 is 0, 1. We are at the state 0, 0. The input is 1. So this is this arc. We stay at the state 0. So 0, 0. We are at the state 1. The input is 0. We stay at the state 1. So 0, 1. We are at the state 1. The input is 1. We go to a state 2. So 0, 1, the input 1, we go to a state 2. And finally, the last 2 rows, we are at the state 2, the input is 1, we go to a state 1, so 0, 1 in this row. And finally, if we are at the state 2 and the input is 1, we go to a state 0. So 0, 0. So this is the completed encoded state transition table. So now that we have this, we can easily come up with the Boolean equations that show the relationship between the next state and the current state and the inputs. So I follow the sum of product form approach. We have one row with value 1 here. So I write the min term associated with this row. It is going to be S1 bar, S0, A. And for S0 prime, we have 3 rows. The first one is S1 bar, S0 bar, and A bar, plus S1 bar, S0, A bar, plus the last one, it is going to be S1, S0 bar, and then A bar. So these are the two equations that show the relationship between the next state and the current state and input for the more FSM. Of course, you can use Carnot map or other forms of simplification to come up with a more simplified set of equations too. So if we do that, these are the most simplified sets of equations. So I highly suggest you do it on your own. You create the Carnot map for 3 variables, S1, S0, and A, and you fill out that table, and if you look closely, you see that using 3 variables, we can have 8 possible combinations. But this table only has 6. So that means that 2 of those rows are don't cares, right? So that helps us to simplify the equations even more. So I highly suggest you do it on your own, but the more straightforward way is by doing the sum of product form. What about the output? For the output, since it is only 1 bit, we basically don't need to have any encoding. It is only 1 bit, so it is either 0 or 1. So that is what we use here. When we are at the state 0, the output is 0. When we are at the state 1, the output is 0. When we are at the state 2, the output is 1. So if I use again the sum of product approach, y becomes S1, S0 bar. So again, this is the straightforward way. You can use the K-map to come up with a simpler equation too, which is going to be y equals S1. Or you can just simply look at this table and see that output y is exactly the same as S1, right? So again, this sum of product form is the most straightforward way without any simplification. If you use the K-map, you can get the most simplified equation as well. So these were the sets of equations for the output logic unit and the next state logic unit for the more FSM. So now let's just see what happens for the Mealy FSM. For the Mealy FSM, the state transition diagram that we came up with only had 2 states, S0 and S1. So that means that the size of the table is going to be smaller. Another difference between the Mealy FSM and the more FSM was in the way that we represented the outputs. So for the more FSM, we represented the output inside the circles. That basically signified that the outputs are only dependent on the current state of the system. But for the Mealy FSM, we show the outputs on top of the arcs. which basically says that these outputs are not only dependent on the current state, but on the current inputs too. So this is another difference that we had in the design of Moore and Mealy FSMs. So now based on this, it is only natural to combine the two tables, both the state transition table and the output table for the Mealy FSM. Because both the next state values and the outputs are dependent on the current state of the system and also the inputs. So if I want to quickly draw the Mealy FSM, so this one is the output combinational logic unit. This one is the next state. Combinational logic unit, we have the inputs, we have this feedback, and then we have this connection too. So as you can see, both next state and the output logic units use the current state of the system and also the inputs. So since this is the case, it is easier to combine the two tables together, so we don't have to write two sets of inputs, even though it is completely possible, right? But it is for more simplification. So since we have here only two states, we only need to have 1 bit for the encoding. So these are wrong, so we only need 1 bit, and that's something that I considered here too in the table, but this is by mistake here. So binary encoding only requires 1 bit to represent these two states. S0 is represented by 0, S1 is represented by 1. If we want to use a one-hot encoding, we need to use 2 bits, which becomes 0, 1, and then 1, 0. So now I write the encoded combined state transition table and output table here, and then I fill it out based on the inputs that we have. So if we are at the state 0, which is shown with a binary encoding of 0, and the input is 0, I go to a state 1, and the output is 0. So this is going to be 1, this is going to be 0. If I am at the state 0, the input is 1, I remain in this state and the output is going to be 0. If I am at the state 1, the input is 0, I remain here, so it is going to be 1, the output is 0, so basically this. And then if I am at the state 1 and the input is 1, I go to a state 0, and the output is going to be 1. So now that we have this combined and encoded state transition table and output table, we can write the equation. So S0 prime using the sum of product form is going to be S0 bar A bar plus S0 A bar, or if I factor out A bar, it's going to be A bar multiplied by S0 bar plus S0. So we know that this is 1, so it is going to be A bar. As for Y, we only have one row for which the output is 1. So that means that Y is going to be equal to S0 A, based on the calculations that we had for the SOP approach, sum of product approach. So these are the two functions that represent the relationship between the next state and also the outputs with the inputs and the current state of the system. So again, you can use both sum of product form, product of sum form, Carnot map. The most straightforward way is the sum of product form, but if you use, for example, Carnot map, you can get to a simpler equation. So now, based on these equations, we can easily draw the schematics of both Moore FSM and the Mealy FSM. So for the Moore FSM, what we have is for S1 prime to be A multiplied by S0 or ANDed with S0. S0 prime is basically A bar, and then Y is basically S1. So these are based on the calculations that we had when we came up with the equation, with the Boolean equation. So this is again the next state logic unit. Here is the output logic unit, which is basically no extra gates, right? So no extra gate is still a combinational circuit. As for the Mealy FSM, we came up with equations that were much simpler. For S1 prime, S0 prime, it was A bar, and for Y, it was A S0. So again, this part is going to be the next state combinational logic circuit. This part is going to be the output combinational logic circuit. And as you can see, for this very basic circuit, we basically didn't have any feedback for the next state logic unit, right? And that is something that sometimes might happen. For this example, since it was a very basic and simple example, this is the case. Most likely, if you are working and designing a circuit that is trying to detect more complex patterns, then this usually don't happen. So I highly suggest you do it on your own. For example, design a circuit that is able to detect this pattern, or 0, 1, 1, 0, right? And see what is the difference between a Moore FSM design and a Mealy FSM design for these type of circuits. So now that we have seen this, we can quickly take a look at the timing of these two circuits and see whether they produce the result at different times. So here what we have is that we have a pattern of 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. I think here we need to have like another 0. So this is the pattern that we have as the input, and as you can see, we have 3 cases of 0 followed by 1 happening in this sequence. So we have a clock that is going from 0 to 1 and 1 to 0 indefinitely. We reset the system. So when we reset the system, we both go to a state 0. Then we read as 1 0. On the next edge of the clock, for the more FSM, we go to a stage 1. The same happens for Mealy too. In Mealy, we also go to a stage 1. On the next edge of the clock, since we have detected a 1 as the input, the more FSM goes to a stage 2. And while we are at the stage 2, the output is going to be 1. While on the other hand, for the Mealy FSM, since we have a direct connection between the input and also the output logic unit, as you can see, if I want to highlight this, so you see the output of the more FSM becomes true later than the output of the Mealy FSM. So the output of the more FSM is completely synced with the positive edge of the clock. But the output of the Mealy FSM is not. And that is because we have this extra path that goes directly from the input to the combinational logic circuit that is calculating the output for us. The same happens here too. So for the second instance of 0 followed by 1, again, a Mealy FSM produces the result sooner than a more FSM. The same here too. So the output for the more FSM is always synced with the clock. At the basically a few nanoseconds after the rising edge of the clock, this thing happens. But for the Mealy FSM, that is not the case. So depending on the problem that we want to solve, either more FSM or Mealy FSM can be preferred. So now that we have seen some examples of both more FSM and Mealy FSM, let's just summarize all the steps that are needed to design such finite state machines. So the first step is to identify the sets of inputs and outputs that we have for our system. So this can be either inferred from the problem description or it is given specifically or explicitly. Then we need to come up with the state transition diagram for our circuit. So depending on whether we are designing a more FSM or Mealy FSM, this state transition diagram can be a little bit different. For the more FSM, we use circles to represent the state. We show the output inside the circles, and we show the inputs that basically cause transitions on top of the arcs between the circles. For the Mealy FSM, what we have is that we use circles to show the state, but since the outputs not only depend on the current state but also the inputs, we show both the inputs and outputs of the system on top of the arcs, and we use a slash to separate between the inputs which appear on the left and the output which appear on the right. Based on the state transition diagram, we then write the state transition table. So that is the initial step for the state transition table. We use the name that we gave the states. Then, since those names are abstract, we need to come up with an encoding. So each one of these states has a binary value, a unique binary value associated with it. So you can either use a binary encoding, which is more straightforward, or you can use a one-hot encoding, or you can just completely choose random binary numbers. As long as they are unique, that is fine. So now that we have come up with the state encoding, for a more FSM, we write a state transition table with the state encoding, and we write a separate table for the output. Again, if needed, we need to encode the outputs too. Remember, for the traffic light example, we had to encode the traffic light output as well. For the Mealy FSM, what we need to do is to write a combined state transition and output table. And the reason for that was, since both the next state and the outputs of the system are dependent on the current state of the system and the inputs. So even though you can do this using two tables, but it is easier to do it in one table. And then based on these tables, these encoded transition table and output tables, you use the techniques that we learned from previous sections of the course. Sum of product, product of sum, Carnot maps, axioms, theorems, whatever technique that you know, to come up with the Boolean equation for the next state and output logic. And finally, based on those Boolean equations, you can sketch the circuit schematic.